Hey everyone, welcome to this week's video lesson, which is on the geography of solar system. So there's nothing too fancy about it this week. Um, Ultimately, we just want to get a baseline understanding of the solar system from the sun outwards all the way to the Oort cloud. And if you're not familiar with this stuff, that's fine. I'll give you just what you need to kind of have a good grasp for everything for the rest of the course. If you're a planetary science student, an astronomy student, this will all be very easy to understand for you. It'll all be information you probably already have from first year astronomy or planetary science courses. But the idea here is that I want everyone to have a basic understanding of the geography of the solar system, which is essentially just what is in the solar system, which we talked a little bit about last week in the formation of the solar system, but also where is it? And that helps us have a better grasp and understanding of where we can go, where we can't go when it comes to robotic versus human exploration. Some places are just too far altogether. Some places depend on how long of a time you have, and some places obviously depend on the environment. So this will be a helpful, I hope, baseline understanding to help explain, why have we only explored the surface of Venus very limitedly in the 1970s versus, the surface of the Moon and Mars being explored much more with robotic spacecraft. Why is it so difficult to get to Mars and get humans on the surface? All that stuff, I hope will be a little bit clearer by the end of this lesson.
If we could open up the sun, we'd see layers of dense hydrogen gas, hundreds of thousands of miles deep. And at its center, the core, the sun gives birth to light. Forged in one of the most violent reactions in the universe, nuclear fusion.
The specific nuclear reaction that powers the sun is fusion. Fusion of hydrogen into helium. You take two hydrogen atoms, you ram them together, and what's left over is a helium atom.
It sounds simple enough, but it's not.
It's actually hard to get two atoms to fuse. Two protons have the same charge, they're both positively charged, they want to repel each other.
Protons don't like to get close together. They have to come together with a huge amount of energy or velocity to get close enough to begin to fuse, and that's very rare.
To force protons together takes immense amounts of heat and pressure, generated by the invisible hand of gravity. The sun contains 99.8% of all the matter in the solar system. That's a lot of mass. All that mass pulls the sun together with unimaginable gravitational force.
But with gravity crushing things down, things get close enough together, and nuclear fusion happens.
In this nuclear compactor, hydrogen atoms slam together 100 million quadrillion times each second. Some of these collisions are so powerful that atoms fuse, releasing energy.
When the protons come together, to bind together, they lose a little bit of mass, and that mass gets converted into energy. And every second of every day, about 5 million tons of stuff is being converted to energy. It's amazing.
Obviously, first and foremost is the sun. It's the center of our solar system. It's what everything in our solar system orbits around. And it's obviously the largest object in our solar system. So you would have learned obviously about this in the formation of the solar system lecture. Just a little bit more information about the sun and why it's important to understand some things about the sun and its activities. Because it affects not only life on Earth, obviously it affects things in orbit around Earth, and it does affect space exploration. It affects whether or not there's solar energy available to spacecraft in certain moons and planets. It obviously affects whether or not spacecraft will function as they get further out into the solar system, and it obviously affects whether or not humans would be able to sustain some sense of health and viability in the solar system. So obviously, I hope you know the sun is immense, 4.3 million kilometers equatorial circumference, which is 109 times that of the Earth. Its mean radius is about 430,000 kilometers. And a lot of this isn't really going to mean a ton. We don't use these kinds of numbers on a regular basis, so they're just big numbers. I find it helpful to think if I am, for some reason, curious about the size of the sun. If the sun were hollowed out and you wanted to fill it with Earths, you would need 1.3 million Earths. And that's probably one of the more helpful ways just to think about the size of the sun in terms of its volume being 1.3 million times that of the Earth. Obviously, that indicates how large it is. Last week, you learned why it's so large. It is the primordial entity of our solar system. It is where a vast majority, 99% of the material and energy in our solar system went and stayed. It's mostly made of hydrogen and helium, which is no surprise because that is the materials. Those are the materials that were most abundant in the proto solar system. A couple things the sun does as well, helpful to think about at least. The solar system is an environment, and in that sense it has dynamic activities happening, and one of them is solar weather. So the solar system, yes, this space is empty, there's nothing going on in a vast majority of it, but there is solar weather, which is to mean there's changes in energy, there's changes in temperature in different parts of space, and that can be important if you're operating spacecraft or if you're going to another world and you want to know whether or not your spacecraft will have access to solar energy. A couple important things in terms of solar weather are solar winds, which are a constant stream of subatomic particles. So subatomic particles are constantly streaming out from the sun to varying degrees and intensity. So that can provide a source of propulsion. They are subatomic particles, so they have mass. So if you capture that mass, it could give you energy. But it also just helps you think about the solar system being more than just empty, even though it is also extremely empty. Another thing to think of with the sun, and there'll be a video to explain this, is the interaction between the solar wind and Earth's magnetic sphere is incredibly important. Now, visually, we get to see the northern lights, which are like a small kind of side effect of solar winds hitting Earth's magnetic field. But without Earth's magnetic field, those solar winds would essentially strip the Earth of its atmosphere and would douse us all in extremely powerful radiation that would make life on Earth impossible. So there's a very important interaction there between the sun and the Earth. And then a couple other key things I just want to talk about: solar flares, which are large releases of X-ray radiation and energy, and they travel at the speed of light in all directions from the sun into the solar system. So when a solar flare happens, it's essentially like the sun burping out in all directions. And then there are coronal mass ejections, which are large masses of particles, so mass, ejected in a single direction, and these are traveling slower than the speed of light. So in terms of these things, coronal mass ejections or solar flares affecting Earth. Solar flares travel at the speed of light, so much more difficult to adjust to in terms of how much leeway we have. Coronal mass ejections travel much slower than the speed of light, so we have a firmer understanding of when there might be some what we call intense solar weather in the Earth's environment or Earth's atmosphere. Beyond that, yeah, a key thing to think about in terms of why we explore some planets and not others, or some moons and not others, is that interaction I talked about between the sun's energy and a planet's magnetic field.
In the not-too-distant future, scientists may be able to simply scan a star for Earth-like planets and find the signature of life there.
we can look right at the light from a little planet around its distant star. And that opens up a whole range of possibilities for us to not just detect the planet, but to study the planet.
I mean, this all sounds like science fiction, but there is a reality to this. We have a scientific method to actually determine whether there is life on another planet.
Life is one thing, intelligent life, another altogether. That requires billions of years and a powerful force field like the one we owe our lives to every day. If an alien astronomer were to file a report on our home solar system, they might make a surprising observation. Because of all the 8 planets that orbit the Sun, they could easily conclude that 2, not 1, were suitable for life. It's an easy mistake to make, because the Sun has 2 planets within its Goldilocks zone, the Earth and Mars. Both planets have surfaces warm enough for liquid water to pool on. But while the Earth is blessed with warm, liquid oceans, Mars is dry and dead. The one crucial difference between these 2 planets could be the key to finding truly habitable exoplanets: a magnetic shield. Our Sun is constantly hurling deadly radiation out towards us. Only our magnetic shield, the magnetosphere, saves us. Without it, the solar wind would blow our atmosphere away, and without an atmosphere, liquid water could not exist on the surface.
In order to have liquid water, not only do you need the right temperature, but you need the right pressure. You know, if there were no atmosphere here right now, even at the same temperature we are today, all of the water would boil off into vapor immediately.
So where does the Earth's magnetosphere come from? And why doesn't Mars have one? Actually, in the past, both Earth and Mars had magnetospheres, but Mars lost its around 4 billion years ago, and with it, the potential for life. Both the Earth and Mars were born into a realm of violence. Asteroids smashed into their surfaces, turning rock and metal into a molten mass. As they started to cool, a solid crust formed on the surface. But the molten metal below churned as the planets turned, inducing a magnetic field which rose high up above the surface of both planets. At the same time, active volcanoes pumped gas into the space around each planet. Protected by the newly formed magnetic field, these gases built up into thick atmospheres, creating the air pressure for liquid water to run on the surface. For over 100 million years, both Mars and Earth were warm, wet paradises, primed for life to take off. Then, quite suddenly, Mars's magnetic protection disappeared. The solar wind blew its atmosphere into space, and its oceans boiled away, leaving the dry, sterile red rock we see today.
Okay, so that's the Sun, its interaction with the Earth. Mars is talked about there. And again, the Sun is more than just the giant thing in the middle of the solar system that we orbit around. It's active, it's a giant ball of energy, and that energy has an impact not only on us on a daily basis, but on everything we do when it comes to space exploration. Now let's talk about moving away from the Sun and into the solar system. Obviously, we're going to talk about planets and moons. I think this was touched on last week with the formation of the solar system. You know, you could divide the entities in the solar system all you want in different ways. The primary way it's done right now is that there are 8 planets. These are major or larger bodies orbiting around the Sun. We'll talk about what their specific definition is. And then there's a host of other things, obviously the moons of each planet, a whole bunch of asteroids, a whole bunch of comets. We'll talk a little bit about asteroids and comets when we talk about the Kuiper belt and the Oort cloud, but we won't focus a ton on them, though they're discussed in the readings. But we'll focus largely on planets and moons. The solar system contains 8 planets that we're aware of. The current definition for what a planet is that is most accepted, and this is debated to an extent in the astronomy and planetary science community, but some people argue it really doesn't matter how you typify these things or how you categorize them. Ultimately, what matters is that we have a good understanding of them, and some of them do certain things and some of them don't, so we might as well categorize them. Other people want broader definitions that would, in an extreme example, argues that all spherical things should be considered planets in our solar system, which to me is not particularly helpful as a categorization, but the argument is that it would provide more reason to focus on other bodies rather than just the 8 that we're most interested in. But to me, it's not, we don't focus on things just because they're called a planet. To me, what's important is they're close and accessible. They're relatively accessible in terms of the environment, and you can access them with either robots or people, and they're interesting. So to me, it doesn't matter if something's called a planet or not. What matters is if we're able to access it and learn about it. Uranus and Neptune, very big, very interesting, but we can't really get there in short order. It takes decades, or at least a decade. And when we do get there, we're often just flying by quite quickly. So that's why we don't explore Neptune and Uranus, not because they're named certain things or not. Anyways, the definition of a planet right now, according to the International Astronomical Union as of 2006, is that it orbits the sun, so an object that orbits the sun. It has achieved hydrostatic equilibrium, which is to say that it has undergone sufficient gravitational forces that it becomes spherical, or is in the process of becoming spherical. And that doesn't mean it has to be a perfect sphere. The Earth is not a perfect sphere. It just means that it is spherical. It is most, if you take all the perfect shapes, what is the Earth closest to? It's closest to a sphere. It is not close to a cube. It is not close to a pyramid. It is closest to a sphere. And then it has cleared out its orbit. And this is something that's pretty highly debated as well. But essentially, it means that the object is the dominant or almost only item in its kind of neighborhood as it moves around the sun. Now, this is debated with things like Mars, which is pretty close to the asteroid belt. It's debated with things like, no, not really Jupiter. Mercury is pretty alone, I would say, actually. But it's something, I mean, even the Earth. The moon is a pretty substantive 1/6 the size of the Earth. So could you really say the Earth is the core dominant entity in its orbital plane or orbital area? Yes, because it's so much bigger than the moon. But no, in terms of the grand scheme of things, where there's something at least 15% the size of it in its neighborhood, that's not as dominant as, say, Jupiter, where nothing in Jupiter's orbit is even close to Jupiter in size. Yeah, so those are the definitions of a planet. Possible 9th planet. Before I get to that, this was all very topical in the late 2000s when this was discussed, and we'll see that this was precipiced or brought to the forefront by the discovery of Eris, a minor planet in the outer solar system in 2005. And that led to some discussions of, okay, is Eris a 10th planet at that time, because Pluto was still a planet? Or is this thing not a planet because it's mixed in with a whole bunch of outer solar system entities, Kuiper belt objects? You'll learn and understand what that means in just a second, but essentially this thing they found, Eris, was quite small. It was spherical. It was orbiting the sun. It was the dominant thing in its orbit, but there's a whole bunch of other stuff there too, asteroids, and it's kind of mixed in with the Kuiper belt. So if it's not a planet, and a lot of people agreed it's not, all those things also apply to Pluto, which is also not very large. It's not really the dominant thing in its solar system. Its moon is very similar to it in size. Its largest moon, Charon, or Chiron, depending how you want to pronounce it. And that led to a discussion of, is Pluto a planet? And the process led to what is the definition of a planet. And by 2006, this was the definition that was landed upon. To this day, some people are very, very concerned, again, with these definitions. I don't typically care. Like I said, the driving force in whether or not, I should say, the people who are very concerned about this feel as if we won't pay attention to Pluto, or we won't study Pluto and Eris and the other minor planets because they're not named planets. They're not called planets, and they think that if we called them planets, people would be more interested in spending money on exploring them. I don't think that's really a great argument. I think we explore things because they're accessible, like I said, because they're interesting. Pluto is interesting, but it's also extremely far away. So I'm more interested in just the physical and geographical properties of the objects in our solar system, and less so what they're categorized as. Speaking of planets, around 2015, there was a lot of discussion about the potential for a ninth possible large object in our solar system, potentially even a planet, the size of Neptune or Uranus. This was hypothesized based on the observations of a number of outer solar system bodies that were moving in a fashion that some astronomers argued was only consistent with the gravitational perturbations, or the gravitational nudges, of a ninth planet out there in the outer solar system affecting these little things. They could see these little things moving, but they could never find this ninth planet. And the argument was that the odds that these little things, these comets and asteroids, we'll say they're all asteroids, the odds that they're moving in the way they are without a ninth planet to these astronomers was very low. Whereas other people argued, no, they're moving like that is consistent with the existing planets in the solar system. It's either an interpretation issue of the data, or it's just you happen to find 9 or 16 objects that are moving a certain way. But if you expand that, you would see that they're not that unique. In the 10 years or so that has passed, the argument that there's a possible a ninth large entity in the outer solar system has largely diminished as a popular idea. It's still, I'm sure, being studied. It was definitely still under study as recently as 2019, 2020, in the last kind of major space conferences I was attending. In the time period, certainly the number of publications on it has shrunk. And we'll talk about this just a little bit at the end as well. Last thing I want to talk about is something we don't talk about in this class, and that's exoplanets. If you're interested, there's a chapter in your textbook that talks about exoplanets. It's quite outdated. Exoplanets is the one area where you would need a new introduction to the solar system textbook, because it's constantly evolving and changing. Whereas, as I've mentioned in previous videos, the textbook I use, though it's from 2010, not much about the solar system has changed in that time. We've learned more and we've observed more, which is covered in other lectures. But the basics that textbook introduces have remained the same, and that's why I use it, because it's the best one, and no one is yet to write a better one. But that's not the case for exoplanets, which is fine, because in this course, like I said, we don't talk about them. Exoplanets are planets that are in other solar systems. So they're outside of our solar system. And they've been, hypothesized forever, as you'll see in next week about the antiquity, or the pre-space age. But they weren't really confirmed until the 90s. And they weren't observed until the 90s, and then they were only really observed in a secondary sense. We were were observing stars that were wobbling, which would imply that there were gravitational forces on them coming from large objects, which could only be planets. And there remains a technique for observing planets in other solar systems, which is to monitor the brightness of other stars, and when that brightness dips, it's an indication that something has passed in front of that star. And if you observe that dip in brightness on a routine basis, that implies that whatever's going in front of the sun or that distant star is routine and regular and orbiting, most likely, which would again imply a planet. So that's what exoplanets are. We don't talk any further about them. If you're interested, definitely take up an astronomy course on exoplanets and take a look. It's very interesting. From the 90s to now, thousands have been hypothesized to have been discovered. None have been directly observed, but evidence of them has been. Small little concept I want to introduce before we talk about the planets. That is the idea of a solar day versus a sidereal day. Again, if you're in astronomy, this is of familiarity, or you already know this. If not, this is something we don't particularly think about on a regular basis and isn't extremely relevant to you unless you plan on doing some astronomy or exploring certain bodies in our solar system where their sidereal and solar days are extremely divergent from one another, unlike the Earth. So what is the difference? A solar day is the time it takes for the sun to be at the highest point in the sky to the next time it's in the highest point in the sky. So what we would call solar noon, the time it takes between one solar noon and the next. So on Earth, it's roughly 24 hours. And that's a solar day. And that's the day we use for pretty much all intents and purposes. However, if you're an astronomer, or if you're interested in which side of a body might be facing you at a certain time, or facing a certain direction at a certain time, which would be of relevance if you're trying to land a probe on it, or a rover, or an astronaut, you would need to be familiar with sidereal days. And that is the time it takes for a body, let's say a planet orbiting the sun, to be facing the same external direction as it was before. So if we look here, I think I can actually draw the Earth, let's say this distant star. The Earth here is looking at this distant star, let's say at noon. And then it spins around roughly 24 hours, and it's looking at that distance again. But if you look here, it's not solar noon yet, and that's because as the Earth rotates, moves this direction, left to the right, it's also moving around the sun. Now this is greatly exaggerated, but you can see that, okay, so it's rotating on its axis this way, and in 24 hours it is once again looking at the sun, but in just under that period it's once again looking at the same position in space. So it's really just, you can look at it as a matter of whether or not it's looking at the sun or whether you're looking out into the solar system. But just imagine if the Earth wasn't moving, these two would always be the same. The Earth would always be 24 hours between when this star is at the highest point in the sky in the night side of Earth, and when the sun is on the highest part of the sky in the daytime of Earth, and then it would spin around exactly 360 degrees in 24 hours, and boom, these two things would be in the same place again. However, in that 24 hours, the sun has moved around its orbit around the sun. So it's not just revolving on its axis, it's moving around the sun. And if you, again, look at this graph without necessarily all my markup on it, you'll see that when the distant star is once again in the same highest part of the sky at night, on the bright side of the Earth, it's not yet solar noon again, and that's because Again, the Earth's movement around the sun distorts these two dates, so they're not always the same. So on Earth, a sidereal day is only 4 minutes shorter than a solar day, so this difference created by the Earth's movement around the sun is only 4 minutes. On other bodies, it's much larger, like Mercury, so that influences obviously the development of missions to enter Mercury orbit or land on Mercury, which we've never done. But if we were, that mission team would need to be familiar with this. So there's a video to better explain this, and I hope it's not too confusing.
A day on Earth is a deceivingly simple concept. Today we'll examine that day on Earth in detail, perhaps uncovering a few surprises. A day is the length of time it takes the Earth to spin 360 degrees on its axis. Or is it 361? Here is a simple model showing the Earth, the Sun, and some background stars. The Earth travels around the Sun in an ellipse, with the Sun at one focus. The model, of course, is not to scale. Let's begin our examination at noon one day. The Sun is directly above the red line. That will be our reference point. Watching from a high vantage point, we see the Earth complete 360 degrees of rotation. But during that time, the Earth has also moved a bit in its orbit. So even after a 360-degree turn, the Sun is not directly above the same point on Earth that it was at the beginning of the spin. It is not noon of the next day. The red reference line needs to spin a little more than 360 degrees to get us to noon. The 360-degree rotation is called a sidereal day, while the noon to noon rotation is called a solar day. Earth orbits the Sun once for about every 366.26 sidereal days, and once for every 365.26 solar days. Not only that, the length of a solar day varies throughout the year, and for two different reasons. First, because of its orbit is an ellipse and not a circle, the Earth moves faster when it is near the Sun and slower when it is further from the Sun. So the little extra amount of rotation that the Earth needs to do to get from noon to noon changes throughout the year. Second, because the Earth is tilted on its axis, the little extra rotation to get from noon to noon is largest at the solstices and smallest at the equinoxes. So solar days grow progressively longer as we move from the equinox, March and September, to solstice, June and December. And did we mention the Earth's spin is slowing down? And the length of the solar day is increasing due to gravitational tides between the Earth and the Moon? The length of the mean solar day is increasing at a rate of approximately 1.4 milliseconds every century. 2 billion years ago, there were about 750 days in a year. Now let's talk about daytime. That period out of 24 hours when it is light outside. Day versus night. Due to refraction and scattering of light by the atmosphere, there can be daylight even when the Sun is slightly below the horizon. But day length is usually about the Sun's disk being on or above the horizon. So the day begins the moment the Sun's disk appears during sunrise, and ends the moment the Sun's disk disappears during sunset. At the equator, daytime and nighttime are equal to within a few minutes. But at distances north and south of the equator, the length of the day varies with the season. with the longest and shortest days being on the solstices. At the poles, once the sun has risen, it stays up for 6 months before it sets again. And during the course of each day, it travels in a complete circle around the edge of the sky. Because the Earth travels at different speeds in its orbit, the Sun is north of the equator for almost 4 days more than half the year, and the length of the average day in the northern hemisphere exceeds the length of the average day in the southern hemisphere by a few minutes. In the northern hemisphere, the Arctic Circle is the southernmost latitude where 24-hour daylight can occur at least 1 day in a year. In the southern hemisphere, the Antarctic Circle is the northernmost latitude where 24-hour daylight can occur at least 1 day in a year. And daylight savings time is like the old man who cut off one end of the blanket and sewed it on the other end to make it longer.
All right, let's get to our first planet. That's Mercury. Mercury's been known about since antiquity. You can see Mercury, at least, well, it just looks like a star, but if you were to observe it on a regular basis, you would see that it's moving across the sky much faster than the other stars. Ergo, it's a planet. It's quite close to us compared, obviously, to those stars. And it's close, very small, and quite bright, but not as bright in our sky as Venus and Mars and even Jupiter and Saturn. So it's been known about, essentially, it has no discovery date. It may have been named at a certain period, but it wasn't just discovered anytime recently. It's very, very small, 15,000 kilometers around. In reference, the Earth is roughly about 40,000 kilometers in equatorial circumference. So Mercury's the smallest planet of the 8. A couple interesting things about Mercury, you've probably heard these before. So its orbital period, or its year, how long it takes for it to orbit around the sun, is 88 Earth days, or 88 days. And its solar day, so if you lived on Mercury, the time between noon and the next noon is actually 176 Earth days. So Mercury's rotating extremely slowly. In fact, it's rotating almost twice as slow, or let's say it's orbiting the sun about twice as fast as it's rotating on its own axis. So the way this is commonly phrased is that Mercury's day is twice as long as its year, which is that, I think about it as if you lived on Mercury, it would be essentially dark for 6 months and then bright for 6 months, is essentially how to look at it. Although it wouldn't be 12 months. It would be dark for half the year and bright for half the year. And the year would be 88 days long. So you get 44 Earth days. If you still kept your Earth watch on you, you'd have 44 Earth days of darkness and 44 Earth days of brightness, back to back. So the other thing about Mercury, like all the bodies in our solar system that don't have a significant atmosphere, it goes back and forth between extreme cold and extreme heat. The average surface temperature of Mercury is 167 degrees Celsius. That average doesn't really mean much. I mean, it's very hot. But the coldest it gets in the shadows there, minus 184 degrees Celsius. The hottest it gets in the sun, because there's no atmosphere to kind of spread out the temperature, so to speak, and because it is so close to the sun, 465 degrees Celsius. So an extremely hot surface that is not really, obviously not habitable. Humans would never go to Mercury. It would be of zero interest and purpose, and they would die instantly, because barring they have pretty advanced technology that is nowhere near right now. They wouldn't be able to survive the extreme temperature changes and the extreme temperatures in both directions. Mercury doesn't have any moons, and it is obviously close to the sun. It's the first planet outwards from the sun. It's 0.4 AU, 0.4 astronomical units from the sun. And that is to say that, I think this was discussed again in the formation of the solar system, an astronomical unit is the distance between the Earth and the Sun. The average distance between the Earth and the Sun is 1 AU. And that measurement is used to discuss distances throughout the rest of the solar system. So Mercury is 0.4 AUs, or 40% of the distance between the Earth and the Sun. In flat out numbers, that's 58 million kilometers from the Sun. Orbital eccentricity, it's actually the most eccentric of the planets, so you don't need to worry about that. None of that is particularly interesting. It's right on the plane of the ecliptic for the most part, has no atmosphere, and has a very minor, very small magnetic field. But yeah, Mercury, in terms of space exploration, you know, we've orbited it with the Messenger mission. We've flown past it, but beyond that, you know, we've never landed on it, which is certainly something that could be done with a probe and a lander, maybe even a rover. And it would certainly be interesting. You look at it, and it's not particularly thrilling visually, but it looks similar to our moon and has geochemistry that is of interest. But it doesn't have an atmosphere. It's not somewhere humans would ever go, and it's not somewhere that we would ever have, you know, long-term sustained robotic exploration. Well, we may in the future, but right now and in the past, we've never had long-term sustained robotic exploration beyond just the Messenger mission, which will be talked about much later in this course. Okay, picking up the pace here because we're half an hour in and we're only at Venus, which is only the second body in the solar system after Mercury, after the Sun, I mean. So Venus, obviously known since antiquity, it's the second brightest object in the solar system at night, the moon being the first one. It's 38,000 kilometers in equatorial circumference, so in terms of how large it is, it's very close to, again, that Earth 40,000 kilometer size comparable. And Venus, like Mercury, but in a different way, is also extremely slow in its rotation. A solar day on Venus is 116 Earth days. So again, a single day on Venus is a third of the Earth's year. So Venus is rotating about its axis very, very slow. However, it doesn't have that flipped thing with Mercury where its day is longer than its year. Its year is 224 Earth days, so it has, you know, a day and a half per year. Is how you can look at it. But 224 Earth days for Venus to go around the Sun. Venus has essentially the same temperature everywhere on it, 460 degrees Celsius, and that's because it has a very thick atmosphere. The thickest atmosphere of all the terrestrial planets, that is Mercury, Venus, Earth, Mars. Venus has by far the thickest atmosphere, and that evens out the temperature around the sphere that is the planet. Venus does not have any moons, and it is 108 million kilometers from the Sun, which is 0.7 AU, so it's close to Earth and most of the time, for periods, not most of the time, but often, Venus is the closest planet to Earth. And sometimes it's Mars, sometimes it's Venus, depending on where they are in their orbits. And that's really all helpful to point out, Venus does not have a magnetic field, yet it has a thick atmosphere. So a lot of what we've learned about so far is that there's a relationship between a magnetic field and an atmosphere being produced and maintained. Venus doesn't have a magnetic field, yet it obviously has surface features, surface processes that are producing enough gaseous material to keep an atmosphere. and that exact process isn't understood yet, but one of the assumptions is volcanic activity is producing enough gaseous, or has produced enough gaseous material in the past for Venus to have a thick atmosphere, even though it doesn't have a magnetic field protecting that atmosphere from solar wind, which has blown it away on other planets like Mars. So yeah, Venus's very thick atmosphere also means that the surface pressure at the surface of Venus is 92 times that of Earth. Which means that when we have sent probes to the surface of Venus, which has only been done a few times in the 1970s by the Soviet Union, those probes were on short order destroyed, but by that pressure and the temperature. They did still capture helpful information. There are pictures from the surface of Venus from the Venera probes, but long-term roving and landing has not been done. It has been hypothesized. We'll see if it's ever done. Humans will almost certainly never go to the surface of Venus. The immense resources that would require, if it even is feasible, are absurd. So yeah, that's Venus. It's essentially a hellscape, but it's Earth with much more atmosphere. All right, this is Earth. Obviously, you know this planet. Not much to talk about. Obviously, everything I've been talking about has been in reference to Earth. So the size of some of these planets, the average equatorial circumference, I've been mentioning, on Earth it's 40,000 kilometers. Orbital period, the time it takes Earth to go around the sun, 365 days. The sidereal day, 23 hours, 56 minutes, which is, we already talked about that. Solar day, the day we use for everyday business, 24 hours. Average surface temperature of the Earth, 15 degrees and climbing. Actually, probably 16 by now. Max and min temperatures, so 70 degrees Celsius typically for the hottest, and minus 90 degrees Celsius for the coldest. Earth does have a moon. The moon, we'll talk about it in a second, and the distance from the Earth to the Sun, 150 million kilometers roughly. So that's another kind of baseline. That's 1 AU. There's a more specific number, 153 something, but 150 million kilometers from the Earth to the Sun. And otherwise, yeah, I mean, the Earth's atmosphere is also used as a baseline measurement. Quite often, 101 kilopascals at mean sea level. And Earth obviously has a magnetic field, which we've already discussed as well. Earth's moon. Again, I hope you know a lot of basic information about the moon, although maybe you don't. In the formation of the solar system, we talked about how the moon came to be. The moon is roughly 1/6 of the size of the Earth in terms of volume, although that's very large for a moon to planet relationship. Pluto and Charon have a similarly large relationship, but most moons are much smaller than their planet. And that's because they're often the leftovers of that region of solar system formation. Because the moon has such a unique formation process, it's much larger because much of its material came from something that was trying to be a planet in Theia and then collided with proto-Earth. The moon orbits the sun by way of the Earth, but it orbits the Earth every 27 days. It does rotate on its axis every 27 Earth days as well. It is tidally bound to the Earth, so what that means is on Earth we always see the same side of the moon for the most part, with a few degrees change each way looking back at us. And like Mercury, it's either extremely hot or extremely cold. So in the sun it's extremely hot, and in the shadows it's extremely cold. It's 384,000 kilometers from the Earth, and really, I think, again, the moon doesn't have an atmosphere. There are moons that do have atmospheres. Ours isn't one of them, and our moon also has no magnetic field. So, as discussed in the formation of the solar system lecture, I believe magnetic fields are a reflection of most likely internal core or geological core processes that we don't think the moon has happening at the moment.
In 1959, the Soviet spacecraft Luna 3 beamed back images of something Earthlings had never before seen, the far side of the moon. We always see the same old side of the moon because the moon rotates exactly once on its axis each time it orbits Earth. If it weren't spinning at all, we'd get at least one 360-degree view of its surface with each lap. If it were spinning twice as fast, we'd also see the moon's entire surface more than once per orbit. But instead, our moon's motions, like the spin and orbit of most other moons in our solar system, are remarkably in perfect sync. This wasn't always the case. Our best guess is that our own moon formed due to a massive asteroid impact, and its initial spin and dizzying 10-hour orbit were almost certainly not in sync with each other, though we don't know which was faster. At such close range, Earth's gravity deformed the moon into a slight oval, with one of its bulges facing Earth. Those bulges quickly swung out of alignment thanks to the moon's asynchronous spin and orbit, but Earth's gravity continually squeezed them back again. What's more, this gravitational tugging would have influenced the moon's rotation rate. If it was spinning more than once per orbit, Earth would pull at a slight angle against the moon's direction of rotation, slowing its spin. If the moon was spinning less than once per orbit, Earth would have pulled the other way, speeding its rotation. Whatever the case, it took just 1,000 years for the Earth's pull to adjust the moon's spin enough that one rotation of the moon corresponded to one trip around the Earth, leaving one side forever locked facing away. We do end up seeing some of that far side because the moon's elliptical orbit gives us peaks beyond its average eastern and western horizons, and its tilted axis causes moon seasons, revealing more of the lunar north or south poles. But those glimpses only add up to an extra 9%, leaving 41% of the moon hidden from Earth. Satellites, starting with Luna 3, have allowed us to map the rest, but it's safe to say that our relationship with the moon is still pretty one-sided.
This is Mars. I imagine you know Mars. Depending on how you look at it, Mars is the most Earth-like planet. It's between Mars and Venus. Venus has too thick of an atmosphere. Mars has too thin of an atmosphere. But I guess if you look at it from a human perspective, Mars is the only other planet you could conceivably survive on for a duration. How long remains to be seen. But yeah, Venus obviously has much too thick of an atmosphere. Mars has about less than 1% of the atmosphere that Earth does. And the atmospheric pressure is extremely low. The availability of oxygen is inconsequential. The humans would not be able to survive on the surface of Earth without spacesuits. So all this to say, it's the most Earth-like, but it's still not very Earth-like, I guess is the point. It's about a quarter the size of the Earth. It's been known about since antiquity as well. You can see it in the sky. It actually has a reddish tinge when you see it with the naked eye, and if you look with a telescope, you can actually make out quite a bit of Mars, as we'll learn about in a future reading. Its year is about twice as long as Earth, which is not surprising. We're talking now about planets that are on the outside of Earth in terms of the solar system. So all of their years, the time it takes them to go around the sun, will be longer because they're further away from the sun. But helpfully, a Martian day is quite similar to an Earth day, 24 hours, 40 minutes. So if you're on the surface of Mars, even though the year is almost twice as long, the days are very similar. So that would be very Earth-like. Average temperature on Mars is only a cool minus 55 degrees Celsius. So I believe I've been in minus 55 degrees Celsius. But I think all of you have probably been in temperatures similar to the warmest day on Mars, which would be about minus 20 degrees Celsius in the sun in the summer at the equator. That would be the warmest, and the coolest would be minus 153 degrees Celsius. But on average, Mars is about minus 55, minus 60 degrees Celsius. It has two little moons. We'll talk about those in a second, Phobos and Deimos. It's 1.5 AU from the Sun, so Earth is 1, Mars is 1.5 AU away. And because it has a similar axial tilt to Earth, so Earth has a 23-degree axial tilt, Mars has a 26-degree axial tilt, which means its hemispheres are unevenly heated, which gives it seasons, which again is something very Earth-like. So yes, Venus doesn't have seasons. Venus has essentially a global weather, whereas Mars has hemispheric weather and seasonal weather, which are very Earth-like. And yeah, Mars does not really have a magnetic field of relevance. You'll see different information on this presented, but ultimately there's lack of a sufficient magnetic field to have protected whatever thicker atmosphere it may have had in the past, or even surface water it may have had in the past. So now Mars is slowly losing its atmosphere, even more so, and is being doused in significant, highly ionizing radiation, essentially across the entire planet. These are Phobos and Deimos. I'm not going to go into great detail in them. They're very small. Phobos is only 70 kilometers around, and Deimos is only what was Deimos? Only 40 kilometers around. So these are very small. They're probably captured asteroids that entered Mars's environment, or orbital environment. There's a possibility they're remnants of Mars from a large collision with Mars, and they're pieces of Mars shot off. We don't know. We've never explored them up very close. There are missions in development that may do that. Deimos is interesting because it's extremely smooth and very small. So for something that size to be so smooth, it's not spherical, and it doesn't have an atmosphere to create that smoothing features. So that's a bit of a mystery. Phobos is kind of unique as well. You can't see it in this, but there's some sort of gravitational forces taking place that are either evidence of it not necessarily breaking apart, but there's some sort of there's ridges and sometimes even linear ridges observed in Phobos that may or may not be evidence of geological processes or tidal forcing from Mars, possibly. So something's going on with Phobos. It's not just a plain dumb rock orbiting Mars. There's some sort of process. And that's enough for planetary scientists to be interested. I think that's all I'll really say about Phobos and Deimos. Neither of them have an atmosphere. I think I mentioned that. Okay, we're not going to talk about all the minor planets, but we will talk about Ceres. This is Ceres, C-E-R-E-S. It's actually in the asteroid belt, so as we move further away from the Sun after Mars, we would encounter Ceres if we chart our path that way. And as you can see, it's spherical, so it's not really an asteroid the way we typically think of asteroids. And on the left is just kind of a visual representation, what Ceres would look like to a human eye. And on the right is a geological map. So that helps show you that there's, well, there you can see a giant depression. So there's geological features, topographical features, I should say. Ceres is discovered relatively recently, 1801, by Giuseppe Piazzi. Yeah, it's an interesting case. We're again talking about those typologies or the way we categorize things in the solar system. It's either the biggest asteroid or the smallest minor planet, although it's not actually the smallest. It's larger than Haumea and Makemake, which are in the outer solar system, which we won't talk about much. There's a bunch of those in the outer solar system, but We don't have time in this class to get to all of them, but I do talk about Ceres because one, the Dawn spacecraft went there, so we've explored it, so it's relevant to a class on space exploration. And two, because it's quite close. It's in the asteroid belt, which also makes it kind of interesting because it's both an asteroid and a minor planet. Yeah, it's very small, less than 3,000 kilometers in equatorial circumference. It, like all of the bodies that don't have an atmosphere, it's either extremely hot or extremely cold, with an average temperature of minus 105 degrees Celsius. It's 2.7 AU from the sun, which the last thing we talked about was Mars at 1.5. So you'll start seeing the distances from the sun really pick up. So Mercury was only 0.4, Venus was 0.7, Earth was 1. Again, it's the basis of measurement. Mars was 1.5. So you've got 4 all within 1.5, and then nothing till 2.7, and then the distances get even bigger between objects. And that's why it's so hard to explore anything in the outer solar system. Otherwise, for Ceres, yeah, there might be a very thin, gaseous, even hesitant to call it an atmosphere, but the Dawn spacecraft did capture evidence of particle material around Ceres, but we don't have enough observations to know to what extent that's global and regular. A famous feature of Ceres is O'Cotter crater, which is very bright. You can see it in the top right there. Another visual representation of Ceres is if you're approaching it. That's an image from the Dawn spacecraft. And you can see that it looks like a white square, but that's O'Cotter crater and a bright white spot, which is either exposed ice or salt or something of that nature that is being excavated from beneath, probably by a large impact. So, again, a body where there's things happening or have happened, but honestly not the most interesting body in the solar system, and given its small size, I'm not sure when the next time we'll fly past it or observe it is, but worth discussing. Okay, so as you may have picked up from the formation of the solar system, Jupiter is a very important planet in the solar system because of how big it is. And it's big because it was the first object to start forming other than the sun, and therefore it was able to essentially gobble up a whole bunch of material. Jupiter's been known since antiquity as well. It's observable with the naked eye in the Earth's sky. It's very large. It's 439,000 kilometers, so 10 times the equatorial circumference of the Earth. It goes around the Earth, or goes around the sun every 12 years. And with Jupiter, a few things worth discussing. The average, the average temperature, it's cold, at least at the surface temperature, but as you enter into Jupiter, the heat would increase because of atmospheric pressure. Jupiter has at least 67 confirmed moons. That number fluctuates, and you may see news articles every once in a while about new Jovian moons being discovered. There's a lot of small things in Jupiter's orbit, which is to be expected based on how it was formed. It's 5 AU from the sun, so twice the distance of Ceres. So like I said, we'll start seeing those AU distances really pick up. Yeah, other than that, I mean, the atmospheric pressure, it varies, but it's roughly 1,000 times that of the Earth. So we don't have a firm grasp, and by we, I mean humanity, we don't have a firm grasp on what any surface of Venus might look like. If there is one, more than likely there's some sort of molten metallic core that's really, the boundary between it and the atmosphere of Venus might be very fluid and nondescript, non-distinct. But if there is a surface of Venus, it's essentially inaccessible to human means, technology, or people. So we would only really ever explore the upper atmosphere of Jupiter if we ever enter in. Another challenge there is the amount of radiation around Jupiter. So similar to the Sun, there's a lot of energy coming off of Jupiter, and not to the magnitude of the Sun, but the radiation around Jupiter is pretty intense. It has a powerful magnetic field, which is an interaction between the solar wind and that magnetic field, which is, reflective and the cause of a lot of that radiation around Jupiter is what I mean to say. And yeah, famously, it obviously has the Great Red Spot, which you can see here and right here and right here. So the Great Red Spot is a large storm, many times the size of the Earth. I think 30 times the size of the Earth. No, that's Jupiter itself, equatorial distance. But I think you could fit, was it 3 or 4 Earths in the storm itself? So just the storm on Jupiter is many times the size of the Earth. And yeah, I think for people interested in Jupiter, that kind of thing is part and parcel of the mystery of Jupiter. As you can also see, the reason I use a GIF for Jupiter is because it's a very dynamic planet. It's spin very fast. That's not real-time spin, but that's just a reflection of how fast it's moving. And it is, yeah, it's dynamic. There's weather on Jupiter. Those clouds, those bands you see, you know, they're constantly changing. In some ways very minute and very small, in other ways very obvious. The Great Red Spot itself is shrinking compared to when it was first found. So, you know, Jupiter's changing. Things are happening, and to planetary scientists and astronomers, anything that has processes, anything that has anything happening is inherently interesting. All right, I'm going to rip through these next 4 moons very quickly. They're called the Galilean moons because they were discovered by Galileo. There are 4 significant moons around Jupiter. I'm obviously not going to talk about all 60 plus moons of Jupiter, but these 4 are worth talking about. Each one of them, to a different extent, has been discussed in terms of sending a mission there. One more so than the others, but they've all also been imaged by the Galileo spacecraft, by the Voyager spacecraft, by the Juno spacecraft. So they've been imaged. Well, they'll come up again later in the course, but very briefly, some basic information about them. Ganymede, the largest moon in the solar system. It's bigger than Mercury, Pluto, and Eris. It has a thin oxygen atmosphere. And it may have a layer of ice surrounding it globally, 800 kilometers thick or more. So that's Ganymede in a nutshell. We'll learn more about it when we talk about the exploration of the solar system. This is Callisto, also a Galilean moon. It's the outwardmost of the 4 Galilean moons, so it's the one furthest from Jupiter of the 4. It's the 3rd largest moon in the solar system, the most cratered object in the solar system. Its surface is a mixture of water ice and rocky material. It's assumed to be dead. This is not a visual image of it. This is a false color image showing some of the surface geology, but if you were to look at Callisto with human eyes, it would look very similar to our moon, to Mercury. It's the oldest unaltered surface in the solar system, which is to say it's probably the thing that has had the least things happening, the least surface processes of anything in the solar system other than asteroids and comets. So for a moon or a planet, it is the most dead. There's just nothing happening. However, there may be oceans under the surface. We'll talk, subsurface oceans is something that comes up a lot in the outer solar system, and Callisto may have one. It also has a thin CO2 atmosphere. So there's interesting materials there, just not a lot of dynamism, not a lot of activity, but still something that would be of interest just because it has such an old surface. So it's actually good evidence of what some of the early solar system activities might have been like. And because it's a Galilean moon, it's quite large and will probably always be higher on the list than other objects its size for observation. This is Io, another one of the Galilean moons. It is the most geologically active, other than the Earth, object in the solar system. we can't necessarily confirm that, so we should say the most geologically active, presumed to be the most geologically active body in the solar system after Earth. If we had more information on Venus and a few other objects, we might be able to confirm that. We also have not observed Io routinely, but we know, even just from observing it from a distance, it is very active geologically. It has active volcanism, so it's one of the few bodies in our solar system where we can say there's confirmed active volcanism and confirmed active liquid processes. If you count surface lava as a liquid, there's liquid-like material moving on the surface of this body, which is very rare. Earth has that, and Europa may have that. Titan has that, and Io probably has that. The volcanoes are not created by the same processes that volcanoes on Earth are. They're actually created through tidal forcing, which is the effect of the Sun and Jupiter playing tug of war with Io, and that push and pull from both Jupiter and the Sun creates tension in Io's core, and that creates the energy for volcanism. It has a thick-ish sulfur atmosphere, obviously reflective of that. And last but not least, Europa. So this is the one this is the moon of Jupiter that gets the most attention. It's the smallest Galilean moon, but it has a young, bright surface. So the brightness isn't necessarily the interesting part, although that is reflective of ice, which means there's water, or a water-like substance. But the young surface implies that something's happening on a regular basis to reshape the surface, right? So we talked about Callisto, where nothing is happening and the surface is very old because nothing happens to change it. On Europa, there's surface changes much more regularly. There's a global ice sheet covering Europa that is hundreds of kilometers thick. The lines and cracks in that ice sheet are created by tidal forcing, again, that push and pull between the Sun and Jupiter. And there's a tenuous oxygen atmosphere. So Europa is thought of to have this subsurface ocean again. So a layer of ice on top, and then inside water ocean. The water would be both similar and very different to the water on Earth. It would still be H2O, but the other things in it would be very different because, as far as we know, there'd be no life in it, which really makes up or really defines much of the chemical composition of water on Earth. But all this to say, this idea of a subsurface ocean with Europa and Ganymede as well is something that really interests scientists looking for life in the solar system, and just to better understand not just life in the solar system, but the history of the solar system and where all the hydrogen and oxygen in the solar system went, how it may have gotten to Earth, and if other bodies have it, how they may have gotten it as well. So unsurprisingly, water, the basis of life on Earth, is always of interest to scientists when it's found elsewhere.
The search for life beyond Earth begins with understanding life on our home planet. And that story, the story of life on Earth, may have begun in our oceans. And that's because, of course, if we've learned anything about life on Earth, it's that where you find the liquid water, you generally find life. So what if I told you that there is an ocean out there beyond Earth? An ocean in our solar system that has been in existence for billions of years. It's an ocean that is perhaps 10 times as deep as Earth's ocean. It's an ocean that is global and may contain 2 to 3 times the volume of all the liquid water on Earth. It's an ocean that exists beneath the icy shell of Jupiter's moon, Europa. So how do we think we know that Europa's ocean exists? Well, it's a combination of using telescopes on the ground and having spacecraft that have flown by Europa and collected data about the surface, about the interior structure, and about the magnetic field around Europa. And the combination of those data sets leads us to a high degree of confidence that this global liquid water H2O ocean is there today, and it's been there for much of the history of the solar system. We used to think that in order for a world to be habitable, you had to be at just the right distance from the sun or whatever your star was, such that you could have a liquid water ocean on the surface. Now, along with liquid water, life as we know it needs two other keystones. The first is the building blocks for life, the stuff you find in rocks. And the second is some form of energy to help power life. And here's where Europa is a real game changer. It is far, far out from the sun, and yet it's got this liquid water ocean. And the reason that Europa has liquid water is because it's orbiting Jupiter, and the tidal tug and pull causes Europa to flex up and down, and all that tidal energy turns into mechanical energy, which turns into friction and heat that helps maintain this liquid water ocean beneath an icy shell. Along with helping maintain liquid water, we think that tidal energy may also allow that ocean to interact with rocks on Europa's seafloor. And it may even give rise to things like hydrothermal vents, which could help provide not just the building blocks for life, but also the energy for life. The question of whether or not life exists beyond Earth, the question of whether or not biology works beyond our home planet, is one of humanity's oldest and yet unanswered questions. And for the first time in the history of humanity, we have the tools and technology and capability to potentially answer this question. And we know where to go to find it. Jupiter's ocean world, Europa.
Saturn, obviously very famous. It has rings. Also known since antiquity because it is also very bright. Goes around the sun every 29 Earth years. Average temperature minus 178 degrees Celsius, so also very cold. Like Jupiter, Saturn has a lot of moons. So these gas giants had a lot of material around them. In Saturn's case, it actually formed rings. We'll learn more about that when we talk about Cassini and the Voyager probes. But yes, some of the material that was around Saturn during the formation of the solar system went into its rings. There are little moons inside of the rings. The rings themselves are a dynamic system of some being thicker and changing and forming and all that stuff. It's 9.6 AU from the sun, so again, starting to see those distances creep up between objects in the solar system. Like Jupiter, very thick atmosphere, not really something that could be visited in terms of the surface. Has a powerful magnetic field, which again is interacting with and in a sense capturing a lot of the solar radiation and creating a highly radioactive environment around Saturn, which makes it for a challenge in flying past it or orbiting it, but not impossible. So we have explored Saturn and its moons. Speaking of Saturn's moons, Titan. We'll only talk about 2 Saturnian moons. One of them is Titan. Titan, very interesting. It's the largest moon of Saturn. It has a thick atmosphere made mostly of nitrogen. The other planet or the other body with a largely nitrogen atmosphere is Earth. It's unclear where this atmosphere comes from, although we know that there would be a lot of gaseous material out in the outer solar system. We don't know why it's at Titan and not somewhere and not with the other moons. Why is Titan kind of unique in that sense, I guess? There's possible volcanic activity on the surface that's never been observed or confirmed. The surface is largely made up of ice and liquid methane. So you'll see images of Titan as we move forward in the class and online. I'm sure you've seen them, or maybe you've seen them. That looks like kind of lakes and rivers. And those are lakes of liquid methane in water ice. So the land of Titan is water ice, and the water is liquid methane. It's cold enough, and it's cold enough for methane to become liquid where Titan is in the solar system. So Titan gets a lot of attention. There's confirmed liquid processes on the surface that we've observed. So we've even landed on Titan. So Titan's the only outer solar system object we've ever landed on. The Huygens probe landed on it in 2005, I believe. And yeah, I mean, Titan, again, extremely cold. An atmosphere, even though it's nitrogen, still not something that we could breathe. But Earth-like in many ways as well, other than the extremely cold temperatures and the high doses of radiation coming from both the Sun and Jupiter. But yeah, something that is very, very of interest to planetary scientists, and we'll have missions going there in the future. Moving along to Enceladus, the only other moon of Saturn we'll talk about. It's the sixth largest moon of Saturn. It's not particularly large. It is very, very bright. It has a thick ice surface. It might have a global ocean underneath that ice surface, but what is interesting about Enceladus is that we've seen material be ejected from what we assume could be a subsurface ocean through the ice layer into space. Which is obviously very unique. So there are geysers on Earth. There are geysers probably, maybe on Venus. There may be geysers elsewhere in the solar system, but none observed. Enceladus has them at the surface, and in very spectacular fashion is ejecting material into kind of the Saturnian orbital environment. There's evidence that some of that material is even contributing to a ring of Saturn. So a very dynamic multi-body process there, if that truly is happening. Materials are being ejected from Enceladus' subsurface and being added to a ring of Saturn. So yeah, Enceladus, something also of interest. There's been ideas to fly, through those plumes when they happen, to see what's in that water. So something to keep an eye on for future missions. I'm not going to spend a lot of time on Uranus and Neptune. This is Uranus, pretty plain visually. There is dynamism happening. It's Uranus and Neptune are both gas giants. They're also sometimes called ice giants because they're so cold. Yeah, I mean, the reason I won't talk about them too much, not because they're not of value to the bigger picture of the solar system, but because they're so far away that we haven't explored them a ton. We've flown past them with the Voyager program. We have images of them, but since then, nothing else. So we don't know a ton about Neptune and Uranus. They're both, they're smaller than Jupiter and Saturn. But they're still much bigger than any of the terrestrial planets. So they're they have a large system of moons as well. I'll talk about one of Uranus's moons. But because of their distance, and that exact distance is 19 AU from the sun. So it is 19 times the distance from the sun as Earth. You saw with Jupiter was only 5 AU, so we've explored Jupiter a lot. Saturn was 9. So, those are way, way closer. I mean, this is twice the distance away from the sun and from Earth as Saturn is. So, it just makes them extremely difficult to explore. From a human exploration side, we'll never put humans anywhere near Uranus and Neptune, at least nowhere near our lifetimes. But we may fly past them again. An orbiter is also hypothetically possible, though I wouldn't hold my breath. So, a lot of our observation of Uranus and Neptune is going to be from telescopes, from space telescopes, and hopefully missions in the future. But like I said, I wouldn't hold my breath just because of their distance, and because of the difficulty in exploring them as gas giants. You can't land on them. You can't even really fly around them for long periods of time because of the radiation around them, and because of the difficulty of entering into orbit in the outer solar system. To get to the outer solar system, you have to fly extremely fast, otherwise it takes forever. But then once you get to these planets, you need to slow down in order to enter orbit, which is a challenge and requires a lot of fuel, and makes the mission very, very difficult. So the last thing I should mention about Uranus is it's tipped over. So a normal planet orbits like this. Something happened to Uranus where it's tipped over, and it's still, you can say, it's rotating like any other planet, and then it's tipped over, and now it's just going like this, but it's essentially corkscrewing through the solar system. And the way to think about that is that it's just a normal planet that's been tipped on its side. Not sure what happened. Neptune's orbit may have shifted at some point, or Saturn's orbit. This was talked about in the formation of the solar system. The dynamics of that are more something for an astronomy course or a physics course in a space exploration course. Not going to say much about Neptune other than I lied. Nothing about any of Uranus's moons, but something about Neptune's moon, Triton. And Triton, moon of Neptune, is really, really interesting. Again, comes with all the same caveats about why we'll probably never explore it in great detail in our lives, but can be explored from a distance, and should be, because it's in a retrograde orbit, which means everything in our solar system goes in that same general direction as the protoplanetary disk, right? That makes sense. The protoplanetary disk was spinning, and the material in it coalesced into bodies, and those bodies continue spinning in the direction they always were. Same with moons that orbit planets. But Triton orbits Neptune backwards. So the most likely reason this would have happened is that Triton was involved in some sort of cataclysmic collision that put it into an orbit that is backwards. You could hypothesize all sorts of other things. Neptune and Triton. Neptune would be backwards then too. In the grand scheme of things, you could hypothesize that Triton is an exo body, so it came from another solar system. Not sure how something the size of Triton would have been expelled from its solar system. That would take a tremendous amount of energy to send it into our solar system and then be captured by Neptune rather than be captured by the sun, which would take a very unique set of circumstances, if at all even possible. But the mystery of why Triton is orbiting Neptune backwards is one worth exploring. Obviously, one of the greater mysteries of the solar system. Could be a captured Kuiper belt object that entered into orbit backwards through collision. Triton's interestingness doesn't stop there. It may have cryovolcanism. This may be seen on Enceladus, Europa, Titan as well, and that is essentially that ice volcanoes may be functioning. So there may be essentially just ice mountains with enough pressure underneath through either tidal forcing or core processes that are creating the pressure that shoots water or through these ice volcanoes. We don't know for sure, but again, something that adds to the intrigue of Titan. This image is from Voyager 2, which flew past Neptune and also collected an image of Triton. It has a nitrous oxide atmosphere and a subsurface ocean, we can assume, hence because of the cryovolcanism. It also has a thin nitrogen atmosphere. So very weird moon in the outer solar system, at least weird in terms of comparing it to other things. All of the reasons it may be different are within the realm of possibility. It's just confirming which one of them is true is something hopefully will happen. This is Pluto. In the bottom left, you'll actually see what Pluto looked like when I was a kid, and that is a 1 pixel sized image from the Hubble Space Telescope. And there was a few images there, but essentially Pluto was not very well known. It was discovered in 1930. It was categorized as a planet because at that time it was unique amongst the solar system. So it was categorized as a planet because it was observed to be round. It was observed to go around the sun. But it was not very well known otherwise. It wasn't imaged in any detail. Astronomers could tell even before Hubble that it was spherical, but what color it was, what its surface was made out of was all mostly unknown, and that changed, as I'll talk about in a second. Few things to talk about. Pluto, very small, 7,000 kilometers in equatorial circumference. Its year it goes around the sun every 247 Earth years. So in our lifetime, Pluto has not had 1 year. No one in this class is 247 years old. Its axial rotation, so its day is 6 Earth days. So if you were on Pluto with your Earth watch and you were still looking at your Earth watch, the difference between solar noon on Pluto and the next solar noon, so one Pluto day would be 6 Earth days. It's very cold, minus 229 degrees Celsius. It has some moons. I'll talk about those in a second. But key defining features of Pluto, it's extremely far away, 39 AU distance from the sun. So Jupiter's 5, Pluto's 39. We still have explored it. We flew past it in 2015 with the New Horizons spacecraft, and that's where this image and a host of other images like it came from. And this image shows off Pluto's famous heart, Utopia Planitia, which is actually a kind of like a glacial field, but covering a significant portion of the planet. And the New Horizons spacecraft, as we'll talk about in the exploration of the outer solar system, discovered that Pluto was way more interesting than people would have thought. There was potentially a thin atmosphere. There was geological activity on the order of a few thousand years. So it wasn't just a totally dead planet where nothing had happened for the last million years. So Pluto was more interesting than we thought, which gave evidence to maybe the outer solar system has more going on than was expected. A couple other things about Pluto that are of interest. Compared to the rest of the solar system, it's very inclined. So the Earth and all the other planets are mostly on the same plane, but Pluto is kind of tilted. We'll see that in a visual next, which is some further evidence that maybe it shouldn't be a planet because it's so weird. But that's not really why it's not a planet, but it is just indication that it's it has like a comet type orbit around the sun, whereas all the other planets and even most of the minor planets are on the plane of the ecliptic, which we talked about in the formation of the solar system. So Pluto, weird, but very interesting. Not sure we'll explore it again in our lifetimes, but possible. It takes about a decade to get there using the fastest technology we can, and usually we just have to fly by again because we're going so fast. But it'd be nice if we could orbit it one day. And again, maybe in our lifetime it's totally possible. We shall see. All I want to mention about Pluto's moons, there's 4 small ones: Styx, Nix, Kerberos, and Hydra. Um, they're interesting. They're really just like asteroids. But Charon, or Charon, is almost the same size as Pluto, and they're locked together, as we talked about earlier, with tidal locking. So they're almost like a dual planet system. So Pluto's a little bit bigger and gives a reason to make Pluto the planet and Charon the moon. But one could argue it's a dual planet system. No one formally does that, and that's not how it's categorized. But it is neat to think of the two of them kind of locked together, orbiting the sun. But Charon has not been imaged in as much detail, and we don't know a ton about it. But yeah, that's the interesting thing about Pluto, and a big reason why it didn't make the third category for the IAU, because it shares its orbit with something almost the same size of it, which is not something other planets do. And this is where we see that visual representation of how eccentric Pluto's orbit is compared to the other planets off the plane of the ecliptic. You can see that the other 8 planets, or the 8 planets, are on the plane of the ecliptic. They're on the same flat table, so to speak, and Pluto is going on and off the table. You can also see it has a pretty eccentric orbit, which is to say at its closest point to the sun is much closer than its furthest point, right? So if you measure these two different distances, they're quite different. It's furthest and it's closest. Whereas many of the other planets, Uranus has pretty eccentric orbit, or elliptical orbit as well. But most of the other planets have a mostly circular orbit. They're still ovals, but they're much more circular than Pluto's, which is very oval, or very eccentric. Okay, so this is Eris, discovered only in 2003. I misspoke earlier. I thought it was 2005. That might have been when the paper was published. But this was the reason, and this is not an image of Eris. We don't have an image of Eris like this. We have telescope images, which are just little, similar to ones we just saw with Pluto from Hubble, just kind of pixel-sized objects. But the discovery of Eris and the fact that it was a spherical, kind of big object, bigger than Pluto, created a lot of debate. Now, we don't know its exact size because it's 68 AU from the sun, so it's almost well, not quite twice, but Pluto's 39 AU from the sun. Now Eris is 68, so it's very, very far away. We think it has one moon at least. Is probably kind of like a Mercury type planet, like just like a rocky terrestrial sphere. We don't know much about it, but we do know it's obviously all of its astronomical facts are understood. Its eccentricity, its inclination, its distance from the sun. We don't know its axial tilt because we can't observe it on a regular basis. I don't think we know its day length either, but it may have an atmosphere based on some observations, but we don't know that either. And this is kind of, as we get this far out in the solar system, this is the state of knowledge decreases, obviously, because things are far away. We can't fly close to them. We've never had anything in the solar system get that far. So it'll be a long time before we understand more about Eris, although astronomers with telescopes and space telescopes will start to fill in some of that information we don't know yet. It won't be to the level of, how much we know about Pluto, because we flew past Pluto. And flying past Eris would be about a 20-25 year journey, and that'd be a tough mission to sell. It's possible, and we'll see if it happens one day in the future, but unsure when or if we'll ever know a lot about Eris. So something to talk about with Eris and Pluto, they're in what's called the Kuiper belt, and the Kuiper belt is like the main asteroid belt between Mars and Jupiter. It is a bunch of material. It's a large region beyond Neptune where there's a bunch of icy asteroids and comets, and these are probably leftovers from solar system formation, and we call these Kuiper belt objects. Pluto was the first ever known Kuiper belt object. We've since discovered Eris, Haumea, Makemake, Sedna, a few other minor planets. Most minor planets are in the Kuiper belt. Obviously, Ceres is not. It's in the main asteroid belt. And the Kuiper belt is kind of the end of the solar system for our exploration purposes. Beyond it, distances get extremely large. We'll never go there as humans. And we may or may not ever get spacecraft out that far as well. We're talking hundreds of AU away from Earth. So there may be stuff out there of interest, potentially a small or large planet, Planet 9, but not necessarily, and that's not where astronomers focus on it, planetary scientists less so. And you can see here in the image, Eris goes in and out of the main Kuiper belt. Pluto is within the main Kuiper belt. And there may be other objects similar to Pluto and Eris in there. They're just very hard to find.
We're just coming to grips with a stunning fact. Over 90% of our solar system begins where the planets end. By the time the sun's light reaches out that far, it's desperately weak. But we knew something was out there because it kept sending us visitors, comets. It was proposed that they came from a mysterious disk out beyond the orbit of Neptune, but no one thought it would be proven.
The Kuiper belt was theoretical. It was thought to exist, but it was also thought that it would be too hard to observe. You're talking about objects which may be 100 miles across, but they're billions of miles away. Trying to find something that's much, much smaller would be incredibly difficult, and no one really thought you could do it.
In 1986, a team of astronomers based at Hawaii's Mauna Kea Observatory decided to prove them wrong.
I'm a bit of a hoarder. These are the notes that we took while we were observing. I used to write lots of things in a notebook to try to keep track of everything that was happening on the mountaintop. Here's the name of the telescope, the 88-inch telescope on Mauna Kea, also known as the Rust Bucket. Visitors to that telescope always think it's the ugliest thing they've ever seen. It's painted brown, it looks like it's totally rusty, parts of it are rusty. So it's a horrible looking telescope, but we use it for all of our work.
If they could locate an object beyond the planets, it would have to inhabit the ghostly Kuiper belt. For 6 years, they found nothing. It was like trying to find a rusty dime in the state of Texas.
We spent many, many years looking for objects in the outer solar system. Lots of pain, frankly, lots of disappointment.
You have to really have some respect for the scale of objects. Yes, we can see stars that are hundreds or thousands of light years away, but they're these giant glowing objects. How do you see something that's only 100 miles across and it's dark, it's not giving off any visible light of its own? That's why finding these things have been difficult.
Kuiper belt objects are made of mostly ice. So you'd think they'd sparkle like icebergs.
We're in a volcanic country, so some of these icebergs are actually dark, covered in ash.
And they're a perfect analogy for a Kuiper belt object.
So I really wanted to get close to this one, but my guides just told me that this one's too big. We can't get close, it might flip over. All right, we found a really cool one. It's really dark. Let's get over here. So, you see how black this thing is on the outside? Well, comets are also black, but actually, they're even blacker than this. We think that comets typically are blacker than asphalt, blacker than tar.
The ink-black Kuiper belt objects stayed hidden for half a decade. Then, one summer night, Jewett and his team spotted something, and the solar system would never be the same.
So here's the log sheet, the notes that we keep while we're observing. 29th of August 1992. We started as normal, looking at the images as they came out of the telescope, and found this first object.
It was a single, tiny dot, moving very slowly across the sky, and its slow path showed it was orbiting the sun, but in an orbit that took it way beyond the planets, an orbit that would put it in the mysterious Kuiper belt.
It was moving incredibly slowly across the sky, and therefore was incredibly far away. And we knew, just from the slow speed, we knew immediately it was the most distant object ever seen in the solar system up to that point. Here's this note, SMO, slow-moving object, question mark. So that's the discovery of the Kuiper belt right there, with those three tiny little letters.
In an instant, the Kuiper belt became real, and our solar system became twice as large.
Okay, so that's really it. We're here at the Oort cloud, which is a spherical, conceptual, though real material thing of comets, dust, asteroids, maybe large objects, though probably not, that surrounds our solar system. And between the Oort cloud and the Kuiper belt is probably a whole lot of nothing. You can see our main solar system and the Kuiper belt. Let me do the highlight here. This is the Kuiper belt. Everything we talked about up until the Kuiper belt is in this tiny area, and that's all within this tiny square. And then this is the Oort cloud, and this is essentially our solar system, but a vast majority of it, a tiny part of it, that our interest is vastly here. A vast majority of our interest is in this tiny section. Even though spatially, that everything we know in terms of planets and moons is just this tiny square of our otherwise larger solar system. So that, I hope, helps explain some of the distances involved. You know, interstellar travel to the next solar system is something of science fiction and probably will remain science fiction, certainly for our lives and probably for the next several generations as well. But yeah, that's the solar system in a nutshell, so to speak. Yeah, like I said, I hope you understand now the vast size of the solar system and how pretty much everything we're talking about is really the inner solar system. Although we talk about that as split up, we make our own inner and outer solar system, which is the asteroid belt inwards is the inner solar system, and then Jupiter to the Kuiper belt is the outer solar system, and we don't even really talk about what's outside of the Kuiper belt. Whereas if for an astronomer or for a cosmologist or an astrophysicist, the inner solar system is essentially the sun out to the Kuiper belt, and the outer solar system is all of this, essentially nothing. But it just depends on your point of reference and what you're interested in. So that's the geography of the solar system in a nutshell. And I hope you now have a better understanding of why we've explored some things, why we will explore some things, and why we can't or don't explore other things, because things are far away, things are hard to get to, and some things just aren't possible to explore because there's too much gas, too much radiation, there's no surface, they're too far away, all that stuff. But other things are close, we can access them, and that's why there's so much focus on things like Mars, the moon, well, really those two, but also Venus and the moons of Jupiter as well. So that's where we'll be focusing. The rest of this course is all within this little circle.